All right, today we're going to continue our notes with continuity and one-sided limits. And we're going to, ouch! Let's see if I can continue this without my cat attacking me. Ah. Okay. Ouch. Ow! No. Anzu, I just want to take notes. Okay. We're given a piecewise function here, and we're being asked to find when is the function continuous. And so what we're going to do here is we're going to look at each piece independently, and then we're going to look at the jumping point, and we're going to test for continuity. Negative 2x minus 5 is a polynomial, and polynomials are continuous everywhere. If you were to think about that function, just negative 2x minus 5, that function is a downward sloping line, the y-intercept of negative 5, and it goes on forever. So that's continuous everywhere. Likewise, if we were to look at the middle piece, f of x equals 3, that's a constant function, and it is continuous everywhere. And then the last piece is a cubic function, and I don't know exactly what it looks like, so I'm not going to draw the grid, but the cubic function tends to look like that, and that's continuous everywhere. So each of the three pieces is continuous. We need only look at the jump point where we move from one piece to the next. So I'm going to evaluate the limit as x approaches negative 2 from the left of the function. I'm going to evaluate the limit as x approaches negative 2 from the right of the function. And I'm going to evaluate f of negative 2. And if these three numbers are the same, then the function is continuous. So when I'm approaching from the left-hand side, we're going to be approaching on numbers slightly less than negative 2, which would be the top piece. So we are evaluating for the equation negative 2x minus 5. And through a tabular approach, we could find the value to this. Direct substitution will work as well. Anytime we just plug this number in and get an answer that's ouch, not divide by 0. Ouch! Stop it, cat. We do direct substitution, and if we get an answer that is not a divide by 0 error, then we're good to go. So if I stick negative 2 into this equation, I'm going to get 4 minus 5 equals negative 1. So on the left-hand side, we're approaching a value of negative 1. When I evaluate from the right-hand side is this bottom piece, numbers slightly larger than negative 2. So we'd be evaluating the limit expression on x cubed minus 6x plus 3. And plugging in negative 2 does not cause any problems as far as a divide by 0 error. So we can go ahead and do the direct substitution route. Negative 2 cubed and minus 6 times negative 2 plus 3. That's going to be 8. Negative 8 plus 12 is 4 plus 3 is 7. And then finally, we evaluate the function at negative 2, and really this should be, since our function name is h, call this h of negative 2, my mistake. H of negative 2 is 3. Because the three numbers disagree, the function is not continuous. Not continuous at x equals negative 2. More specifically, we can say there is a jump discontinuity. As we can see, the left limit and the right limit disagree because the limit as x approaches negative 2 of the function does not equal, let's go negative, the limit as x approaches negative 2 from the right of the function. That is the reason that we have a discontinuity. So we could have stopped as soon as we saw those numbers were not the same, but we went ahead and did all three just to preserve the idea of doing all three all times. Okay, so an important thing to remember is Polynomials are great because they're continuous on all real numbers. They're continuous everywhere. A good tip on the next one is rational functions, the ratio of two polynomials, are continuous on their domain. So this function f of x is continuous everywhere except at -2. At -2, this function is not continuous because that is outside the domain of this problem. So the question here is asking us if the function is continuous and f of x equals this when we're, that should be when x does not equal -2. Let's fix that. Then what is f of -2? So in other words, our function is a piecewise function. Let's write it out. It's equal to this when x is not -2, and it's equal to some other unknown value when x is -2. And we're going to want to have continuity. In other words, the limit as x approaches -2 of the function better equal f of -2. That way the two-sided limit equals the function and continuity is established. Well, we know f of -2 from our piecewise functions, so we're going to define that. But we do not know what this is. So let's work at solving this out. X approaches -2. I'm going to go ahead and factor the numerator. If I stick -2 into this equation by direct substitution, I get a divide by zero error. However, when I'm evaluating limits, I'm allowed to do a method called factoring and canceling, and I notice that the x plus 2 on top and bottom cancel out, and I have the limit as x approaches -2 of x minus 2. So by making that canceling error, I can evaluate the limit. -2 minus 2 is -4, and that is the value of k. So my left side limit equals -4, my right side limit equals -4, and now my function, in order to maintain continuity, I'm going to set my function equal to -4. So the answer to this question, f of -2 equals -4. All right, moving on to example 5. Without graphing, justify why the two functions are continuous everywhere. Well, let's just say, is the function continuous at a value c? Continuous at c. We're going to ask that question. So in order for the function to be continuous at c, the limit from the left has to equal the limit from the right, has to equal the function at c. These pieces all need to be the same value. And by direct substitution, if I stick c into this expression, I'd get c to the 2/3, which does not cause a divide by zero error. And so we're pretty safe here because the divide by zero errors is what causes discontinuity or jumps. But since this function doesn't have a jump, it's not a piecewise function, then we're good. Again, if I stick c into this one, I get c to the 2/3, and if I evaluate f of x at c, I would get c to the 2/3. So f of x is continuous at every value c. If I do the same thing or before we jump to part b, let's just look at what this function looks like. it's the cube root function squared. It winds up looking something like this. So visually we can see that this is continuous. This is the analytical support of that. E to the x, if I take the same approach, if I do the limit as x approaches c from the left of e to the x, well, that would be e to the c. If I do the limit as x approaches c from the right of e to the x, well, we direct substitute that in and we get e to the c as well. And finally, if I evaluate, in this case it's g of c, I would get e to the c. Because all three things are the same value, we get this function as continuous. And from our parent function we know e to the x looks like that, and that's a continuous curve as well. So this process of proving whether functions are continuous everywhere or not actually is useful, but I think it's probably better to just remember the difference between functions that are continuous everywhere versus continuous on their domain. We've already seen that polynomials are continuous everywhere. And we've also seen that rational functions are continuous on their domain. And then we want to see what other functions out there. So another type of family that we've seen, exponentials, like 2 to the x, 3 to the x, 4 to the x, e to the x. Those are all exponentials and they're continuous on all real numbers. Logarithms are continuous on their domain. And if you think about a log function, graphically we have a vertical asymptote that the function connects closely to. So that's why it doesn't exist over here in the negative area, and so we can't say it's continuous at negative numbers. I've listed out a couple more here. Sinusoids, as in sine and cosine, so maybe cosinusoids, but sine and cosine, they're continuous everywhere. Odd roots, we're talking like the third root of x or the fifth root of x, as opposed to over here, even roots, square root of x, fourth root of x. We can't take the square root of a negative number, so there's a spot where the function does not exist, and thus restrictions to the domain. Thus it is continuous only on the domain. Okay? Also tangents, cotangents, secants, and cosecants. And you might recall that these are ratios, like tangent is sine over cosine, so it can be kind of classified as a rational function. Likewise, secant is 1 over cosine, so it's kind of a rational function. By far and away, recognizing polynomials, exponentials, those help speed up a lot of problems. So here we've got example 6. For what values is the function continuous? Well, c of x plus 1 is a polynomial, so this will be continuous everywhere, and therefore continuous. And cx squared minus 1 is a polynomial, and therefore continuous. So the only spot that this function could be discontinuous would be at the jumping point 3. So if we are talking about exploring continuity of this function, we would look only at the jumping point 3. And we would want these three values to be the same for a continuous function. Well, if I'm approaching 3 from the left, that would be using the top piece, and I can plug in 3 for x, and I get c times 3 plus 1. If I'm approaching 3 from the right, that would be where 3 is larger than 3, sorry. We could plug in 3 for x, and then g of 3 uses the top piece as well, and we get c times 3 plus 1. This is the limit evaluated. If I want to establish continuity, if I want to force continuity, then what I would be saying is these two numbers need to be the same. 3c plus 1 must equal 9c minus 1. And technically we would need the third piece as well, but the third piece is 3c plus 1. So if we solve that equation, we get 2 equals 6c. If c equals 1/3, g of x is continuous. So to recap what we did, because it was kind of a messy problem, we're trying to make g of x a continuous function. There's some unknown value of c that would make g of x continuous. So first I established that the top piece is continuous everywhere because it's a polynomial. The bottom piece is continuous everywhere because it's a polynomial. So the only thing that we're going to do is we're going to explore when these two curves jump from one piece to the next. Okay. Visually, what we've got going on is, now that I've got the value of c, the top piece is a curve that winds up looking like this, and it stops at 3. And the bottom piece is a parabola that has been shifted down, so it probably does something like this. I'm dotting this half because it doesn't exist, and then it starts existing. Okay. So we've got the top linear function and the bottom parabolic curve, or quadratic curve. If I let the limit from the left equal the limit from the right, I am forcing continuity, and so I set those two equations equal to each other and I solve for c, and in the case of c equals 1/3, we would have a continuous function. Every other value of c would cause a discontinuous function. Essentially it would adjust the steepness of this line or move the polynomial in some way, or sorry, the quadratic, so that they no longer meet up. Okay. This is a good challenging question, the sort that you would find on the AP calculus test in a free response portion. Sometimes multiple choice, but it is an in-depth problem. Really hits hard on understanding of continuity. Okay, we're going to do it again for example 7. In this case, we're trying to find the value of k that makes the function continuous. So I'm going to say the limit as we approach 0 from the left has to equal the limit as we approach 0 from the right. If these two are equal, then we have a continuous function. Because the top is a sinusoid and therefore continuous everywhere, and the bottom is a polynomial and therefore continuous everywhere. So we need only look at the jumping point. The limit as x approaches 0 from the left would be using the top piece of the piecewise function, and the limit as x approaches 0 from the right uses the bottom piece. And we can evaluate limits by direct substitution, provided it causes no divide by 0 errors. So this becomes 4 plus sine of 0, which is 4. And this becomes 0, I'll write it out, 5 times 0 plus k, and we get 4 equals k. So this curve is continuous if we let k equal 4. Okay. And visually we can think about this one to see if it's true. Our top curve is a sinusoid with a midline at 4. 1, 2, 3, 4, and we graph only on the left-hand side. So there's the sinusoid. The line is now a line with a slope of 5 and a y-intercept of 4. So 1, 2, 3, 4 with a slope of 5. So that makes the function continuous. All right, I know that was a doozy of a video. I hope that some of it made sense to you. And in truth, for my pre-calculus students, like, this is primarily for the people who are tending to move on to the calculus class. Having a deep understanding of this will be helpful for them. All right, thanks for watching. Have a good day.